recording. Right. So let us look at this whole sequence of events and the relationship between all these angles more closely now. So let's look at the first event, which is the refraction from air to glass. Suppose that's happening this way. Yes, Samarth, I'll scroll up, but it's the same diagram above. Okay, and I'll be labeling the same values. So this is the first thing that is happening. So here, if I draw the normal at the point of incidence, so always generally we refer to the angle between the two surfaces which are refracting as the angle of the prism with the symbol capital A. Now we'll call this point of incidence over here as, let's say, P. So the angle of the incident ray with respect to the normal, that is the angle of incidence, and the first refraction, this angle becomes the angle of refraction R1. So for this first refraction, this glass has a refractive index mu, let's say on either side we have air. So we have sine I is equal to mu sine R1. So given I, we can calculate R1 from this. Okay. Now the geometrical thing starts. So at the second surface, when this light is incident over here, you see that there is a relationship at the angle of incidence here. Now consequently, we call the angle of incidence instead of I, we call it R2. So this R2 has a relationship, okay, with this. So let's understand that relationship also. So if the second point of incidence, we are calling it the point Q, let's say. Okay. And this point where the two normals meet, we call it S, let's say. Okay. And this angle, let's say, we call it something beta. Okay. So we can see at the second refraction, the angle of incidence is R2. So we'll come back to that. But before that, we have beta is equal to 180 degrees minus R1 plus R2. Okay. And if this point here is A, we can also see for quadrilateral PSQA, okay, beta plus A will become 360 degrees minus 90 plus 90, because these other two angles are 90. The normal, so this angle is 90. This is a normal, so this angle is 90. Okay. So that gives us an important relationship here, that beta is 180 minus A. So when we combine this relation with this relation, we get another important relation here. We get that the sum of R1 plus R2, whatever be the angle of incidence, it doesn't matter, is always equal to the angle of the prism. This is independent of the value of angle of incidence. Just note down to this point. So solving anything related to deviation by prism, any numerical, you have to remember this simple idea that the sum of these two internal angles R1 and R2 is always equal to the angle between the two surfaces. So going back to the previous section for a moment, you'll see it's the same diagram now. Okay, so now coming back to this. Now further, when I look at the second refraction, let's come to this. So the angle of refraction is what we call the angle of emergence. So this is bending away from the normal. So this becomes the angle of emergence. And for the second refraction, we have the relation that mu sine R2 is equal to sine E. Now also in this, we can see that if we produce this first ray forward, incident ray forward, so this is the deviation that it has suffered, delta 1. And if we produce the final refracted ray or the emergent ray rather backwards, then this is the deviation that this one has suffered. That's the same as this angle here. So this is now the net deviation. This is what we're looking for. This is the net deviation. So now you can see that this refraction is giving us a deviation, which you can see in that diagram is I minus R1. And this refraction, which you can see in this diagram, is giving us a deviation E minus R2. It's also clockwise. Okay. So that is why the net deviation is delta 1 plus delta 2. Also, you can see that from triangle, if you name this point where they meet, say T, you can see that the exterior angle is the sum of the interior opposite angles. So we get the formula for the net deviation as I minus R1 plus E minus R2. So that is I plus E minus R1 plus R2. And you know that R1 plus R2 is a quantity which is independent of the angle of incidence or anything else. It is just the angle of the prism. So this becomes the final relationship. So for a given angle of incidence, we will have a certain amount of deviation. But to calculate the deviation, we need the angle of emergence, for which we will need to use the two equations that we got from Snell's law. So it's an entire process. Okay? Given the angle of incidence, use the first refraction formula to find R1. Then from R1 find R2 using the fact that R1 plus R2 is equal to A. Then again use Snell's law to find the angle of emergence, and from that finally you can find the net deviation. So this is the process of finding. Okay, so the idea is that given We know the angle of the prism, we know the refractive index of the glass. Now, for some specific angle of incidence, first use this relation mu or sin I is equal to mu sin R1. So from this we'll find R1. Then use the relation that R1 plus R2 is equal to A. So from this we find R2. Then again use Snell's law that mu sin R2 is equal to sin E. So from this we find the angle of emergence. And then finally from that we find the angle of deviation. So this is the process. So in the whole sequence of steps, okay, the laws of refraction, I mean, Snell's law used is very obvious, but these two are the important geometrical relations. Keep in mind this one and then finally this one. Okay, so let's look at an example problem numerically. So this is a diagram above which refers to the same problem, but given that the angle of the prism is 45 degrees and the refractive index of the glass is root 3, approximately 1.73, and a ray of light is incident at an angle of incidence equal to 60 degrees from one side. So find the net deviation. And draw the ray diagram with all the corresponding rays or corresponding angles, etc. So we'll have to use a scientific calculator because we'll get some odd values of sin I, etc., which we'll need to calculate. Okay, let's check out the solution. I'll take you step by step through the calculations, Aman, so you can check your answer. So the first step that we do in this sort of calculation is we calculate the angle of refraction for the first surface. So here we'll see that if this angle of incidence is 60 degrees and mu is equal to root 3. Okay. Then we have sine 60 is equal to root 3 sine R1. So R1 comes out to be sine inverse half or 30 degrees. So this angle comes out to be 30 degrees. And also we can see that the first refraction results in a deviation of 15 degrees. Now we come to the second refraction. So when we drop a normal here, we'll see that the angle of incidence will become 15 degrees. So this angle of incidence here, this will become 15 degrees. So using that, we can see that so now again we'll use Snell's law to find out the angle of emergence. And then we are done. Once we have found the angle of emergence, this angle here, so this is where I'll use a calculator. But you can always find sine 15 degrees also like this, that so always use this formula. Also, but here I'll just make use of calculator. So sine 15 is approximately 0.26. So from this E will come out to be sine inverse of about 0.45, which will be approximately 26.6 degrees. So I made use of a calculator twice. Okay, at the exam you'll either be given values which you know, or you know, the corresponding sine and cos values will be given to you, sine and sine inverse in this case. Okay, so in this step and again in this step I made use of a calculator. So anyhow, so I'm getting the angle of emergence as 26.6 degrees approximately. So from that I will get the net deviation as something like this. Okay, so hope this is clear. Now the next concept we'll understand related to this to further understand the behavior of deviation with respect to angle of incidence is the principle of reversibility applied here. So we can understand that through this example only, that we have a particular angle of the prism. In this case, we have taken the example that this is 45 degrees. Okay. And a ray was incident at a particular angle of incidence. And it emerged out at a particular angle of emergence. So when the ray was in this sense, this angle of incidence and this angle of emergence was like this. So if we took the angle of incidence as, for example, 60 degrees, we got the angle of emergence as 26 degrees. So the sequence of events that happened, 26.6 or whatever. So the sequence of events that happened is that, I is equal to 40, sorry, I is equal to 60 degrees. That gave us R1 is equal to 45 degrees. So 30 degrees. Okay. That gave us that R2 was equal to 15 degrees. And that gave us that emergence was 26.6 degrees. Now we apply reversibility. If the light is incident like this, then what will happen is that this will become my angle of incidence in the second case. And this will itself become the angle of emergence. So if instead my angle of incidence is equal to 26.6 degrees, okay, then sine I2 is equal to mu sine R1 prime, let's say. Okay, so this formula will give me my R1 prime as this value, 15 degrees. So this ray has reversed its path. And then the fact that R1 prime plus R2 prime is equal to A will tell me that R2 prime is 30 degrees. Okay. And then mu sine R2 prime is equal to sine I. Let's write this as prime so that we're using the same notation. So when we take it in reverse, and the deviation we'll see will be again will be the same. So this is true for any set of values. Okay. Hence, what happens is, okay, so just make a note of this. So basically for any angle of incidence, let's say X, if solving everything gives us an angle of emergence equal to Y, and therefore the net deviation comes out to be X plus Y minus A, then for an angle of incidence equal to Y, solving everything will give us the angle of emergence is equal to X. So it will give us the deviation of the same. So it will give us the same deviation. So that means any particular value of angle of deviation will correspond to a set of two possible values of angle of incidence. In this case, the deviation of 41.6 degrees can happen from incidence at two different angles, either incidence at 60 degrees or angle of incidence being 26.6 degrees. Okay, so when
So could you scroll up for a second?
okay. Uh,
Done, sir. Thank you.
yeah. Shikhar, to answer your question, I2 was the angle of incidence which I had taken in the second case, okay, which I have later replaced as I prime. So I've interchanged I prime and E prime as E and I, what was earlier. So that is showing the reversibility principle. So what was in my first case, first pair of values, what was my incident ray? In the second case became my emergent ray, because what was my earlier emergent ray became my incident ray. So of course this will also work if I do it in by changing the side altogether. So if
So that should be E prime is equal to 60 degrees, no?
sorry, which was 60 degrees?
The E prime,
Uh,
you've written I prime.
yes, E prime will become 60 degrees. Yes. Oh, sorry. Yes. My mistake. This should not be I prime. Just make a correction, people. This should be E prime. This one. Okay, yeah. So in the first case, if this I was 60 degrees and we got the emergence angle as 26.6 degrees. Okay. Now, one I showed you by just reversing this diagram, but instead of reversing this diagram, if I reverse the situation also, the same thing will hold true. So if I make the angle of incidence like this, then this diagram will kind of change like this. But so this time if I make the angle of incidence this value, what was the angle of emergence? Then without doing the calculation only, I can be sure that the angle of emergence now will be what the angle of incidence was. In both cases, the rays will deviate by the same amount. So here, if I was getting delta as 41.6 degrees, here also I'll get delta as 41.6 degrees. Okay, that is that way. So now if I understand that as a behavior of deviation as a function of angle of incidence, I'll see that any particular value of angle of deviation, okay, comes for a particular angle of incidence, let's say I1, and then again it repeats for another particular value of angle of incidence, I2. So if I is equal to I1, then E will be equal to I2. Whereas if I is equal to I2, now emergence will be equal to I1. But in both cases, the deviation will be the same. It will be I1 plus I2 minus E. Okay, so for example, when we had that situation where the angle of the prism was 45, mu was root 3, I1 was 60 degrees, I2 was 26.6 degrees, and the deviation was 41.6. Okay, so this sequence will repeat in such a way that the graph follows this kind of a pattern. And there is only one particular value of angle of incidence at which the angle of incidence becomes equal to the angle of emergence. And when we achieve that particular angle of incidence, we are at the minima of the graph. So from this, we understand that the condition for the minimum possible angle of deviation condition for this is that there is a unique angle of incidence such that at that angle of incidence, the angle of incidence becomes equal to the angle of emergence. So now we will develop a formula to calculate this minimum deviation also for a given prism. By given prism, we mean that we know the angle of the prism and the refractive index. That we can calculate what is the minimum deviation possible. Of course, we can also calculate the maximum deviation. I'll come to that also, but first the minima is the more important thing. Okay, so let us look at this condition for minimum deviation more closely now and how we calculate it. So the condition for minimum deviation is that there is a symmetry between the angle of incidence and the angle of emergence. So that symmetry now extends. Yeah, Vineet, I'll take you back to that graph. Let's understand this condition more first. So that condition of symmetry will therefore extend to R1 and R2 also. The moment angle of incidence is equal to angle of emergence, R1 will be equal to R2. And therefore R1 equal to R2 will be equal to this thing, A by 2. This quadrilateral will also have that symmetry. So we have the condition that I is equal to E. Then we'll have the condition that R1 is equal to R2. So become E by 2 because then this deviation angle becomes the minimum. So even this other triangle that we had drawn earlier, this also has a symmetry. So now you can see for the first refraction, we have sin I should be equal to mu sin E by 2. So basically angle of incidence should be sine inverse of mu sin E by 2. And therefore the minimum deviation will become this. Yeah, this one. So as a reverse of this, we can see that uh, So we have this interesting relationship between refractive index of the material of the prism and the angle of minimum deviation. So let's absorb this information with a simple example. If the angle of the prism is this time 60 degrees and the refractive index of the prism is again √3 or 1.732, then find the angle of incidence for which the deviation is the minimum deviation, and find the value of this minimum deviation. So see, this one is an easy calculation. So just try and work this out, please. Yes, very good, Mike. That's correct. Viraj, that's correct. So while everyone is working this out, I will just scroll up to the previous section. So angle of deviation versus angle of incidence. We'll also talk about this value where the maxima occurs. We see this situation also. And what exactly we mean by maximum deviation. But yes, Nikita, that is correct. Okay, so let's move back to the question. And through this question, you'll also understand the concept of maximum deviation, or what happens if we change the angle of incidence from the condition of minimum deviation. Okay. So first of all, for the condition of minimum deviation, we will see that we want the angle of incidence to be equal to the angle of emergence. So we want R1 to be equal to R2, which is E by 2. So in this case, R1 is equal to R2 will become 30 degrees. Okay. So now we have sine I is equal to mu sine R1. So from this we have, so we see that the angle of incidence will be 60 degrees, which will be equal to the angle of emergence. And so the minimum deviation will become 2 into 60 minus 60, because in general it is like this. So the minimum deviation angle will also come out to be 60 degrees. And this situation will basically look like this. Now, here what the bottom of the prism is like, it doesn't matter. So it need not be, just because this angle is 60 degrees, it need not be an equilateral prism. It could be that this is cut in a different way altogether. So it's really irrelevant what these other two angles are. It doesn't matter, because they are not involved in the refraction in any way. They don't affect the values. But what is important here is that the angle of incidence should be such that this symmetry works out, that the angle of emergence comes out to be the same. And for that to happen in this particular case, what we are seeing is that I want the angle of incidence to be 60 degrees. So that this is what happens. That gives me, so this also comes out to be 30 degrees. And incidentally, I just get this net deviation also as 60 degrees. That's just because of the values being like this. It need not always be the case. Okay, now for example, from this figure, what will happen if I make the angle of incidence larger? If I is made 60 degrees plus something, okay, then R1 will also become 30 degrees plus something. Okay. So R2 will become whatever that is. Okay. So the angle of emergence will tend to decrease. But the overall deviation will increase. So delta will now become greater than delta minimum. Okay. But similarly, reverse of this, if the angle of incidence is decreased, okay, then this will also decrease. So this will increase. Okay. And the angle of emergence will correspondingly increase. So again, reversibility. Now, what is the limiting situation? Okay. So here, since we are decreasing the angle of incidence, the angle of emergence is increasing. So the limiting situation will either correspond to maximum value of E possible, which is E tending to 90 degrees, which is a grazing emergence. Okay. Or the limiting situation for this, which is corresponding to maximum possible angle of incidence, which is the grazing incidence, I tending to 90 degrees. So like that. So let's understand those two situations. Which is the limiting case of either I tending to 90 degrees, grazing incidence, or emergence tending to 90 degrees, which is grazing emergence. So just quickly make a note of this, then we will discuss this numerically through the previous example only, and I'll show you how this works out in terms of the graph. So that will give you the entire range of deviation that is possible for refraction from the two surfaces of a prism. If we want that there is refraction from surface 1 and then again surface 2 and the ray emerges out instead of total internal reflection happening, then there is a certain range of angle of incidences which is possible, and for that range of angle of incidences there is a range of angle of deviation. So we've seen the condition for minimum deviation. Now we'll work out the condition for maximum deviation from the two limiting situations. One is from the minimum deviation condition, if we start increasing the angle of incidence gradually, how we can reach a limiting situation. And the other is if we start decreasing the angle of incidence, how we can again reach a limiting situation. Yeah, Shikhar, explain it with a numerical example, then it will become clear. Just write this down. Okay, so scrolling up stage. Acha, the minimum deviation condition, yeah. But that was the numerical example we did, na? So as an example of this one's application also, you can see that suppose we were to apply this here, the question would be like this, that if for an angle of prism equal to 60 degrees, the minimum deviation is also equal to 60 degrees, then find the refractive index of that particular. So you just have to apply this formula that in this case you get it as sine 60 divided by sine 30. So that would be root. Okay. Now moving on, this maximum deviation condition, limiting case. So let's consider grazing incidence. Okay, so we have made I almost tending to 90 degrees. So what that situation will look like, let's understand, and let's also do the calculation for that. So we'll take that same prism that we had of angle of the prism 60 degrees and mu equal to 1.73 or approximately root 3. Now let's make the incidence almost grazing. So if this ray is almost parallel. So it's basically parallel. Okay. So then we have to apply the reversibility concept to the critical angle idea. Okay. So what we'll realize is that the angle of refraction here will become critical angle. This is so sine 90 degrees is equal to mu sine R1. So this R1 will actually become the critical angle for that glass here. You can see R1 will be sine inverse of 1 by mu. In this case, sine inverse of. So if I do this calculation again, save time, I'll quickly work this out using a calculator. In this case, I will get the angle of refraction. So 1 divided by root 3 will give me about 0.577. And then when I take sine inverse of that, it will give me about 35 degrees, 35.3 degrees. So first of all, this is what my refraction at the first stage will look like. This will become critical angle. So now my second refraction's incident ray this angle of incidence this R2 will become approximately like this. So now mu sine R2 is equal to sine E. So let's see how much this works out to be. So this will be about sine inverse of 0.723 should then be about Olympiad emergence is this. So now let's see what deviation that is giving us. So to understand the deviation, I have to basically just produce this all the way back here. So this is only so, so this deviation that I'm getting now will be 90 plus 46.3 minus 60 degrees. So that will be about 76.3 degrees. So on my relationship between deviation and angle of incidence for this particular situation, we had seen that we were getting minimum deviation of about 46 point, what was it, 41.6 degrees. No, sorry, we are getting 60 degrees now. $60 for an angle of incidence equal to 60 degrees. Now from there, if I increase the angle of incidence, I can take it all the way to about 90 degrees. But that will give me a deviation of about 76.3 degrees. On the other hand, I can also see that this value which I'll get, this will actually be this angle of emergence. This will be 46.3 degrees. So I can either take I as tending to 90 degrees, then emergence will be equal to 46.3 degrees. Okay. Or I can take the reverse of this. I can take I as 46.3 degrees, which will give me angle of emergence as 90 degrees, which is the grazing emergence. So this is the other, but these both will give me my maximum delta of 76.3 degrees. So that case would look like this. If I just reverse these rays, or I drew the diagram symmetrically from the other side, then the emergent ray would be grazing. So the angle of emergence would be 90 degrees. So this is the example for the angle of the prism being 60 degrees and the refractive index being 1.73. Getting delta minimum equal to 60 degrees at angle of incidence equal to emergence equal to 60 degrees. And we are getting delta maximum equal to this much for this case. Hey, beta, that was for the other one where the angle of incidence was 45. Sorry, angle of prism was 45. This is the case where the angle of the prism is 60. So if you take the angle of the prism as 45 instead, you will get some different condition for delta maximum. You'll get so for this limiting case now you'll see that for I prime equal to 46.3 degrees, you will get R1 prime as what the R2 was over here, 24.7 degrees. Then from that you will get R2 prime, the second angle of incidence as this one, what is it? 35.3 degrees, which is the critical angle. So finally, the emergence will happen at grazing. So that's just the reverse of this diagram. And you can later take some values and check yourself. Like, if you take something in between here, like if you take an angle of incidence of, let's say, 53 degrees, you'll get some other deviation which is in between these two. Or if you take 40, if you take, let's say, something else like 47 degrees or 50 degrees or something like that. Or if you take angle of incidence as maybe 75 degrees, then you can check out, you'll get some different value of delta, but it will always be between these, between the maximum and the minimum. So anyway, this is a very simple thing, but the calculation involves a bit of painstaking work, so it takes time to understand this. Okay. Now from this, we move on to the final part of geometrical optics, which is optical instruments. Now this is a part which is limited only for JEE Mains. It is not there in JEE Advanced.
It will be included in boards.
Sorry?
Boards में भी होगा ना?
Boards and NEET also.
Okay.
So to understand optical instruments, we have to first of all understand a few new terms. Like we have to understand the concept of angular size. Okay. And from that, the concept of angular magnification. Okay. So an angular size of an object has to do with the linear size as well as the distance at which the object is observed. So if the eye of an observer is receiving light from some object like this, then the total angle subtended by that object, that becomes the angular size. That is theta. Okay. So I mean, even if it is some odd shaped object like this, and this is the location of the eye, the overall angular size will be just the total angle spanned by this. So that is why you have that optical illusion of a nearer object appearing much larger. So if we have an object of this kind of size, which is here compared to the eye, okay, but we have an object which is technically much larger, but at a much larger distance. So this is object 1, this is object 2. You will see that object 1 spans a larger angle, even though it is smaller. So actually, to the naked eye here, it will appear like, so even though size of 2 is greater than size of 1, but angular size of 1 appears to be more. But since we have binocular vision, that is, we have 2 eyes, so we are able to also see 3D depth perception. So we are able to resolve this issue and understand that, okay, actually the object 2 is much further away from us. But if we had monocular vision, then we might not have been able to resolve that. So that is what happens when you take photographs. Okay? And there's no depth perception in the photograph. There's no reference for the depth perception. The image is such, then you're not able to make out whether an object is actually small or large, because you're not able to make out whether it's near or far. So building can appear as tall as a person in an image like that. You've all seen those images. Okay, so now what an optical instrument does, and now along with this concept of optical size, I mean angular size, we also need to understand another concept of least. Actually, before that, understand that for a very small size object, like we are observing fine print on paper, or we are observing something microscopic, like a dust particle or something. Okay, what happens is that because the size of the object is comparatively small, if the distance from the eye is x, then we can take the angular size as more or less tan theta. Or if h is the height of this object, then theta is h by x, where h is the height of the small object. Maybe. So nearer the object is brought, the larger it appears. However, the problem here is that when we bring it nearer, there is a limit to which we can bring it. This is the least distance of distinct vision. For the eye. Anybody tell me what the value of D is?
30 centimeters.
It's approximately 25 centimeters. Yes. So it turns out that if we bring an object nearer and nearer, it will appear to be larger. But if we bring it nearer than capital D, then even though we'll see it as a larger object in terms of angular size, we will not be able to resolve the image in our retina properly. So ultimately, it's of no use bringing it that close. So this is the closest at which the human eye can successfully focus the image on its retina. Bring it any closer and the image cannot be focused properly on the retina. So the vision is not proper. It will appear blurry. It will not appear like a sharp image. So that is the inherent limitation of the human eye. So therefore, because of this limitation, okay. So because of this limitation now, the maximum angular size for a small sized object viewable to the naked human eye, that is without any optical instrument to help us, that is this. Okay, so this is the maximum angular size to an unaided eye. Okay, so no optical instrument is being used. So the maximum angular size that we can perceive is this much. So now we'll see how we can use an optical instrument, like the most simple of that being a simple hand lens, what we call a magnifying glass, and the most complicated being, multi-stage compound microscopes, and at an even more advanced level, there is electron microscope, but we will not get into electron microscope here because that is having a different technology. We'll talk about compound microscopes, which basically have compound lenses and use a combination of compound lenses. We'll understand how we are able to achieve a larger magnification compared to this reference value. Okay. So for any optical instruments functioning, this value theta naught that we have written, that is the maximum angular size for the unaided eye, that is used as a reference point. So compared to that reference point, how much larger we are able to see the object, that tells us the magnification. Not the type of magnification that we have seen earlier in lenses, which is the linear magnification. But now we'll talk about something else called angular magnification.
Sir, 1 minute.
Okay, so now if we use any optical instrument, and through that we are seeing that small size object, but we are able to perceive that image of that object. So the eye perceives an image A prime B prime of the object AB at an angular size theta. So here this angle will become theta. The angle subtended by the image that the eye is seeing. Okay. So whatever this optical instrument is, we'll see different type of instruments. But when we are looking at this object through the instrument, then instead of the object, we are perceiving the image of the object, and that is both at a larger distance as well as it's having the angular size theta. So the corresponding angular magnification that we have achieved through the instrument, or rather the instrument has achieved, is this angular size with respect to the reference angular size, where the reference angular size was whatever the height of the original object was divided by capital D, where D is about 25 centimeters. Okay, so we will see that there are different ways in which we can achieve angular magnification. Okay. And the simplest way to achieve angular magnification is the example of a simple handheld lens, like when you use a magnifying glass. Or also the case of a watchmaker's eye lens. If you observed anybody who does repair work or any kind of technical work on mechanical wristwatches, they wear a lens on their eye. So they're able to view those very small parts of the mechanical watches much more clearly and work with them. So that basically consists of a simple converging lens of focal length f, such that the focal length f should be less than the value of capital D. So now to achieve this kind of magnification, what we need to do is we need to place the object at some position which is within the focal length. So in that case, what will happen is that the refracted rays will be slightly divergent in such a way that the image will appear to be somewhere here. And you can see that the optical size of the image, the angular size of the image will be this theta. So I'll draw a diagram more carefully with it. So this is the ray that goes through the pole undeviated. And this is the ray parallel to the principal axis, so it goes through the focal point. So this is the angular size of the virtual upright image. So we've kept the object at a distance x. Let's say the image appears at a distance x prime. So you can see theta, which is h prime by x prime, is the same thing as h by x. So the angular magnification, which is theta upon theta naught, becomes h by x divided by h by d, which is ultimately telling us that the angular magnification achieved is d by x. Now remember that the focal length is less than d, and here x will be less than d, so obviously it will be greater than 1. So for example, if we have something which has a focal length of 20 centimeters, and we kept an object at a distance of, let us say, 15 centimeters, then let us find the angular magnification it will achieve. And let's also find the position of the image. So one thing that we have to take care of here is that x prime should be greater than d, so that the eye can focus the image of A prime B prime, which it is seeing on its retina. So the human eye is observing this from this side, and to the eye, the object AB seen through the lens is A prime B prime at x prime. So that A prime B prime here is the virtual upright magnified image of AB. So x is less than d, but that doesn't cause a problem for the eye over here, because the eye is not seeing AB. Eye is seeing its image A prime B prime, which is at x prime, which will become greater than d. So that's what we'll understand through the numerical example also, which I have given below. Okay. That suppose we have a handheld lens of focal length 20 centimeters, and we keep an object at a distance of 15 centimeters. So without the lens, there's no way we could have seen that object clearly, because it's at a distance less than capital D for us. But when we are seeing it through the lens, it will appear to be at a different position. Okay. And hopefully it will appear to be further away than capital D, and it will achieve an angular magnification in the process. So imagine we are observing a very small object whose height is like half a millimeter or something. So hardly perceptible at a distance of 15 centimeters, at a distance of 25 centimeters, but it achieve a good angular magnification through this process.
Sir,
Yes, very good. So you can see that's correct. The answer you have sent. Aman. Is greater than 1. This angular magnification till C will be greater than 1. Why? Because X has to be less than B. Okay, so that's we'll see through this. Okay. So first of all, when we use the UV formula, we'll get 1 by V minus 1 by minus 15 is equal to 1 upon plus 20 with the proper sign convention. So we'll get V as how much? Minus of this. So minus 60. So you can see that the eye is very comfortable in this case. X prime is 60 centimeters. So you can comfortably view it. That is to focus on the retina, but also it's achieving the angular magnification of how much? It is achieving an angular magnification of D by X. So 25 centimeters divided by 15. So almost 2, 1.67, that kind of angular magnification. So similar is the working principle of simple microscope. So microscope uses a combination of 2 lenses. We'll just take a few minutes to complete this. So if the eye is over here, so this particular lens that we look into, that is called the eyepiece. And that has a focal length of Fe. And the object is kept in front of another lens that is called the objective lens. So this has a focal length F0. And the object is kept at some distance, let's say X1. So now X1 is going to be between F0 and 2F0. So that what happens is that this lens, it produces this sort of an image. Of this. So the objective lens produces a real inverted and magnified image A prime B prime such that H prime is equal to linear magnification produced by this into H, where if this distance is y1, greater than 1. Okay. Now this becomes the object for the eyepiece. So now the eyepiece is designed in such a way that, the eyepiece is kept at a distance in such a way that this will form a virtual image. Of A prime B prime, which will be the final image seen by this, by the eye. So that will be the final image. And that final image is at some distance, y2, let's say. So first of all, you have a relation between these two. From here, you have 1 upon y1 minus 1 upon x1 is equal to 1 upon f4. So from that, you can find this. Okay. And then 1 upon V minus 1 upon minus x2 is 1 upon Fe. So that will give us V as minus of y2, such that y2 will be large compared to t. But x2 should be less than the focal length of the eyepiece, which itself is less than this distance of distinction. So now this image E prime B prime, this becomes the object for the eyepiece, which produces a virtual upright and magnified image. A double prime B double prime. That is the final image seen by the eye. So that's why this becomes the final angular size. Okay, so finally, the angular magnification achieved, which is theta upon theta naught, becomes this value. So now you can see it's a similar formula to the handheld lens, but it's multiplied by another factor m naught. So it becomes m naught into d divided by x2. There it was directly d divided by x. So there's a multiplicative factor. So that means the magnification becomes more. So suppose the objective lens is achieving a linear magnification. Here remember MO is the linear magnification by the objective lens. That M equal to V by U formula using that. So suppose that linear magnification is only 5 or something. Okay, so then it will become 5 times the angular magnification we could have achieved by using the eyepiece as a simple handheld lens, but using it in combination with the objective and creating a simple microscope. Therefore, we are achieving 5 times the magnification. So like that, a compound microscope consists of more layers of lenses, or actually what happens is that the actual lenses used for the purpose of the objective lens and eyepiece are compound lenses, which consist of combination of lenses, but the principle is similar. So there are layers of magnification which are happening such that the final image that we see appears to be at a large distance y2 compared to the least distance of distinct vision. So we are able to see it comfortably, but it subtends a much larger angle compared to the reference angle theta naught. So we are getting a large amount of angular magnification. And yes, in the case of simple microscope, the final image is inverted compared to the original object. But that is not a problem for a microscope, like when you're looking at, let's say cells or, microparticles or microorganisms, etc. through a microscope. You're not really worried about the image being inverted. Okay, so with that, we will conclude today's session because we run out of time and I have another session coming up. This part beta is the application of the lens formula to the objective lens. To the eyepiece. 1 by V minus 1 by U is equal to 1 by F. So now we'll see whatever V we get, that is actually minus of Y2 because it's a virtual image on the same side. So this is the lens formula applied for what the eyepiece is doing, this part. Whereas this is the lens formula applied to what the objective is doing, which is this part. Okay, so we will conclude today's session here, and next lecture we will maybe look at a numerical example of the application of this, but with this we complete geometrical optics. So we will go back to waves after this. We will do a few revision questions from sound and the final part of wave mechanics, and then move on to wave optics. Students of Blue House, you have already had one lecture of wave optics with me, but it will become a revision lecture for you. Okay. the first lecture of wave optics, and from there onwards. So that's it for today's session, people. Thanks for attending and wish you have a nice day.